So good morning everyone. In the previous video I discussed about the Kalman's observability as well as the observability. Now we are going to discuss about the Gilbert's observability. Okay. So in the Gilbert observability, it is assumed that in the given state space model A, B, C, D, the matrix A is not the diagonal canonical form. If the matrix A is in the diagonal canonical form and the transformation matrix is identified, T is equal to 1. Okay, and it can be applied directly without transformation of directly with AT is equal to A, BT is equal to B, CT is equal to C, and DT is equal to D. So find the eigenvalues of matrix A. So if the eigenvalues are distinct, then proceed the next step. If some of the eigenvalues are repeated, then stop, since the given state space model cannot be transformed into diagonal canonical form DCF. And third one, find the transformation of matrix T, which can be using one of the two methods. T is equal to M. In this case, the transformation matrix T is the model matrix of A, or the matrix that is obtained from the eigenvectors of matrix A. Let lambda 1, lambda 2 dot lambda n are the distinct eigenvalues of the matrix A, while m1, m2 and dot m1 are the eigenvectors corresponding to the eigenvalues of lambda 1, lambda 2 dot lambda 1 respectively. Then the model matrix A is given by m is equal to m1, m2 dot m n. So then next, T is equal to V. In this case, the transformation matrix T is the vendor Monday matrix of A. So T is equal to V equal to, so in the matrix 1 1 1 in the first row, then second row is the lambda 1, lambda 2, lambda 3 dot lambda n. Then next it will be increasing lambda 1 square, lambda 2 square, lambda 3 square dot lambda n square, and lambda 2 square, lambda, so 1 cube, lambda 2 cube, lambda 3 cube, like this it will be goes. Finally it will becomes lambda 1 power n minus 1, lambda 2 power n minus 1, and lambda 3 power n minus 1, lambda n power n minus 1. So this is called equal to the vendor Monday matrix. Then next step, find the transformation of matrices AT, BT, CT, DT of the diagonal canonical form is given below. So AT is equal to T inverse of AT. So that is called as diagonal matrix. So AT is equal to T inverse of AT is the diagonal matrix. BT is equal to T inverse of B. So CT is equal to CT and DT is equal to D. Okay. So then next we are going to discuss about the system with distinct eigenvalues is completely observable if only the no column of CT is equal to CT has all 0 elements. To apply these conditions for complete observability, the matrix T inverse AT should be in the diagonal form. So normally the T inverse AT is in the diagonal form usually. So that may be the different, like diagonal form, like different type. This means that eigenvalues of matrix A should be distinct of eigenvalues. Suppose AT is equal to T inverse of AT means it is the diagonal form. This means eigenvalues of matrix A should be in the distinct eigenvalues. And next step, if any column of CT CT equal to capital CT as all 0 elements, then the corresponding state remains unobserved from the output. Okay, suppose CT is equal to CT and all the 0 elements, then we are saying that the corresponding element unobserved from the output. So this is a term to remember. Then if the eigenvalues of matrix A are not distinct, then diagonalization of is impossible. Okay, so then the last one, in this canonical form all the states are decoupled or non-linked each other. So this should remember, all the states are decoupled and not linked to each other, hence for the system to be observable. Okay, observable, each state should be observed from the at least one output. So here the states are decoupled, not linked to each other, so hence the systems are be observable. So each state should be observed from at least one output. Okay, so this is the thing you should remember over in this Gilbert's test for observability. So here you can say AT is equal to T inverse of AT should be in the diagonal form. That means the eigenvalues of matrix A should be distinct eigenvalues. So CT is equal to CT as all zero elements means it is not the remains unabsorbed from output. Okay, so eigenvalues of matrix A are not distinct, then the diagonalization is impossible. So the eigenvalues matrix A is not distinct, then diagonalization of is impossible. Like again, the canonical form is decoupled, not linked to each other, hence the system is observable. So each state should be observed from at least one output. Okay, so this is about the Kalman's test for observability. So both Kalman test for observability as well as Kalman test for controllability and Gilbert test for observability, Gilbert test for controllability. So these are all the things we have discussed over here. So next we are going to discuss about the problems.